Now I'm going to do a couple of finite element simulations to show the difference in performance based on different material properties. We're going to look at spring force, we're going to look at maximum stress, we're going to look at temperature rise, and coplanarity tolerance. Now these are 4 materials I'm going to use and study in the simulations. Important to point out that beryllium copper would be the second one used, and that is what we would consider to be the best spring material out there. But I'm also comparing to some other materials, high-strength steel, and brass and aluminum. Now, no one would ever, in their right mind, use brass or aluminum as a contact material. But what I'm doing in this case, since this is a tutorial presentation, I'm going to take a little bit of artistic license here and use these materials just to show the difference in effect of elastic modulus and yield strength, because these are widely varying in these 4 materials. So if we start off looking at the effect of elastic modulus has on contact force for a given deflection, we have your contact force versus compression curves here for that particular example contact I showed you. You can see the stiffer materials, the materials with the highest modulus, will give you the highest force for a given deflection, and vice versa. So steel gives you the highest force. Beryllium, copper, and brass are very close in elastic modulus, so that will give you very similar performance. And aluminum has a very low modulus, so that would be the least stiff of all the materials. So in this case, you say, okay, we'd like to have a nice material with a nice high elastic modulus to give us good contact force. Now, the other side of that coin is if you have very high contact force, you're also going to have very high stress. And this indeed shows you the fact that the stiffer materials do have a higher stress level than the less stiff materials. Now, it should also point out that these 2 previous examples have been linear elastic modulus, and this is not considering the effects of yield strength or any plastic deformation whatsoever. Now, if we factor in that yield strength and do a nonlinear model with plastic strain hardening, you can see the effect here. The aluminum has a low stiffness and a low strength. So as the force increases, you get to the point where you hit the yield strength, and then any additional deflection does not generate any increase in contact force, but just increases the amount of permanent set.